Yeah. So let's start. Oh, that's it. I'm starting. Oh, hi. So first, let me thank the organizers and Arnav specifically for this very nice workshop, and I'm glad to see here a lot of students. Yeah. So I'm going to speak about an area of computational complexity and how it relates to logic and proof theory. Perhaps proof theory is not the precise term here, it's more like proof complexity. I'm going to show some results, some highlights. I'm going to cover some basic notions, and it's going to be somewhat eclectic collage of results just to give you the flavor of the area. And the basic question is, when I prepared initial version of this talk, it was about the question of what can logic teach us about computational complexity, and specifically in this case proof theory. Fundamental hardness questions, this is how I call the basic lower bound questions in computational complexity about hardness of some computational problems. You can think about it as mostly a representative is P versus NP question. So we have computational complexity. As I said, the fundamental hardness questions are about small time, space, which problems can be computed efficiently, which problems cannot. And as I said, P versus NP, problems that require a huge amount of resources to solve, and whether the question is whether brute force is necessary in some sense, in some precise sense, namely whether we have to search the space of all, let's say, exponential many possibilities or solutions to find a solution to some computational problems. This gives us the questions about separation of complexity classes, as I said, like P versus NP. That's computational complexity. And yeah, of course, those who haven't heard about P and NP, or they don't remember the definition, they can think about it concretely as the following question: does SAT, satisfiability, have polynomial size Boolean circuits? Boolean circuit, most of you know, it's it's basically a computational model with logical gates that computes a function. And you can think about it as a computational model that in some generality can simulate Turing machines. So, but it's slightly more concrete, more combinatorial in flavor, and that's why people a lot of time like to work on this model. Yeah. So the question is, what can logic teach us and tell us about complexity? Complexity is mostly very combinatorial in nature, or at least nowadays, very combinatorial and in some sense also algebraic. It's very mathematical and concrete, while logic, it's slightly, in some sense, the traditional avenue to complexity, but it's not, maybe it's not the let's say the major approach to complexity. And there are several tracks. Maybe there are more, but I've put here several directions in logic that tried to tackle this question, this fundamental hardness questions. Descriptive complexity, finite model theory, it's more or less the same. Implicit complexity, that's just names to remember. And then there is the proof theoretical approach, which Actually, I think, is the least logical one. And I'll show you, in some sense, some examples how it is actually reduced to very concrete combinatorial and algebraic problems, while I'm not certain that the other approach are. So we come from this tradition of proof theory. I don't know how many people know proof theory, but I will discuss some concept and how they relate to complexity from this area. Of course, you can ask questions. But as I said, this is not going to be a technical talk. There's some technical definitions, but it's mostly a survey of some ideas to give you the flavor of the area. So the first order setting, that's the content of this talk. So it's the first order setting is something about proofs, first order proofs, and I'm going to discuss how they are defined, the setup of this this area of which is called bounded arithmetic. And I'm going to show, or at least state, that there is a correspondence between these first order formal systems and the propositional setting. Propositional setting is just the setup of logic, propositional logic that most people learn at the first year. It's just there's no quantifiers. And I'm going to show you some correspondence between this. And the first order setting also leads to questions about the mathematics of complexity itself, namely the question about whether we can prove, and in which proof system we can prove or cannot prove basic fundamental questions in the theory of computational complexity. And what is interesting about this area, what I call the first proof theoretical approach, it's actually mostly proof complexity approach, is that in this area, we can start from the first order setting, but go to questions that are completely algebraic and combinatorial. And we try to understand provability from this direction. And also this algebra combinatorial approach leads to question about mathematics itself. I'm going to give you some examples. So let's try to just be slightly more concrete and understand what is the first order setting. So I'm not going to give much details, but it's going to be it's going to be dealing with the following goal. So the logical theory that characterizes bounded resource reasoning. Yeah, that's what we are trying to define. And in this case, I called it feasible reasoning. Feasible, something that corresponds to a reasoning that corresponds to, let's say, polynomial time. And what can it be? So one thing is we can intuitively explain it as proofs whose concepts are feasible, are polynomial time. So the concepts that I use in each proof can be computed in polynomial time. Right. So the setup here, well, I put an asterisk. It's kind of going to be a somewhat intuitive version. And maybe there are some inaccuracies, but it's fine for this level, this high level. So the idea is quite simple. You want to consider a theory that works with concepts that are feasible, right? So I'm starting with a class of first order formulas, which actually characterize a complexity class C. Complexity class is just a class of functions that that can be computed with some computational model. As I said, maybe small circuits, maybe constant depth circuits, and so forth. So, right. So I can say that the following. I can say that the class of first-order formulas are actually defining a computational class. I'll show you something, some example. And then I can think about the following: C reasoning, reasoning in the class C, in the computational class C, for instance, p-time reasoning, polynomial time reasoning. It's something like the first-order theory for natural numbers. So this will be somewhat weak version of arithmetic, a theory about numbers, piano arithmetic, with big restrictions on the induction and other axioms. And I'm going to add another axiom, the axiom which I call comprehension axiom for C, which is, I'll show you the definition, is just the axiom that says that a set exists in my world if it is definable in the complexity class C. And the third idea is the following. This is the most, these are just definitional, the first two. This is a theorem which is goes back in proof theory probably about 100 years ago. But in the context of bounded arithmetic and complexity, it takes the following form. It is the following. So it's a proof to computation principle. It's called the witnessing theorems. If a theory is weak, then the provably total function have small computational complexity. Provably total is just an intuitive way of calling some specified. It's in a precise manner, more or less the functions that the theory knows are functions, or that it can prove that they are functions. I will show you the definition soon. Sometimes it's called provably recursive functions. So if a theory is weak, then what the function knows as functions actually are very constructive, right? If the theory is weak and it can prove that some function is indeed a function, then I can translate it into a statement that says that the computational complexity of this function is small. In our case, I call the small c. I call the complexity class C. So if the theory knows that something is a function, I know that the function is in complexity class C. And that's the most, maybe the most helpful or the major, one of the central ideas in bounded arithmetic, the witnessing theorems. Now let's see, yes. Yes, the highlight, it's good, yeah. If a theory is weak, no, it's not a definition, it was the stipulation, it was the condition. Yeah. It depends, it's a parameter basically on C. If it is weak in the sense that as it goes weaker, it's going to be smaller computational complexity. Now, yes. Now, if it is not, for instance, if it is not weak, then you cannot characterize the complexity class of the provably total function. It might be some kind of, maybe they are recursive, but they don't have a complexity bound, right? That's the standard arithmetic. So if they are weak, very weak, in our case, it's going to be bounded quantifiers, then you get something that usually is weaker than P or NP. But if this theory is not weak, you'll get something that is maybe recursive, but not It's not within the realm of our complexity world. It's not a definition. It's just a stipulation that I put here. Not really. I'm going to just describe this. The only concretization is this one. And that's it, yeah. But I'm just giving you the slogan of bounded arithmetic. The theories are very weak, some of them. And in this case, this is going to be C, is going to be constant depth Boolean circuits. Right. And implicitly, you might extract the definitions from this slide, although I wouldn't say this is the optimal way to understand the definitions. Right. So, and here is some detail. So two sorted. So I'm going to concretize this as the theory of two sorted theory. So it's you can think about it as follows. And these are the theories based on, it's based on a paper by Zambella from the 90s, but it's mostly the approach taken in a very nice book by Steve Cook and Fong Nguyen from 2010 about this area. But there are other approaches, but they are more or less equivalent. But they are different in notations. So this is the two-sorted theory for efficient reasoning, where C here is actually AC0, so constant depth circuits, so Boolean circuits. But you can take it further up to, let's say, P, polynomial time. So the two-sorted theory is this: number sorts over natural numbers and string sort. String sort, these are finite strings, X, Y, and Z in capital letters. And string here is actually encoded by a set of numbers. So it's a finite set of numbers, which are the characteristic function of the string. So if I have, I'll show you an example. Yeah, here. It's range over, formally, it's range over finite sets of numbers encoding binary strings. So if I have 0 to 5, it encodes the strings whose 0 to 5 are the bits are lit and the other are not. So it just tells you which bits are there. So that's just an encoding. It's not important to remember this. So you have to think about this. There's numbers and there's strings. And then the natural, and then there's the language. The language is 0, 1, the constant of numbers, and then plus times for these numbers. And then you have a string. This is a string variable. And then you have the function which says what is the length of the string. The length of the string, and because the strings are finite, and then there is equivalent, less than, and this guy is the function that tells you whether the ith bit, right, this is the input, the ith bit is lit in the string X, whether it is 1 or whether it is 0. So it's a predicate. And then you have natural axioms for symbols. I don't provide them. They are just the obvious intended model of these functions. And then you have the following comprehension axiom, right? It just says that a string, finite set, exists in the world if it is, in the language of strings, decidable in C. Right. So don't read the English, the plain English, but this is quite simple axiom. It says that if phi is more or less in the class C, AC0, then there exists a set X such that defines precisely the, so if phi Z is true if and only if the Z's bit of X is 1. So it's basically defined this trick. But this is just for those who likes to see the somewhat concrete definition, it's not necessary to understand or remember this. Right. That is the. So as I said, the setup is the following. Which function? This was the setup, and the question is the following. Which function does the theory TC, so I call it a theory for reasoning in complexity class C, essentially prove to exist, right? So that is another concept from proof theory that goes we have it here in bounded arithmetic or in this setup. So fx is definable in the theory by a formula phi, and that is the definition if the theory can actually prove this. Namely, it proves that for all x, for all string x, exist, this is exist exclamation mark, so exist a single y such that phi x y. Right, so it just says the following. The function f is definable in the theory if I have a formula that defines the binary relation of this function. So that's the only detail, I think, most of the details that I'm going to give about this setup. So the witnessing theorem, or the, as I call it here, proof to computation principle, is the following. A function f is definable by some set of circuit, some set of formulas that basically are in the language of C, I call it sigma B1, in TC, if and only if f is computable in C. Well, I don't know what is the background. I presume that a lot of people here have very strong background in logic. What do you think? I don't know if you've heard of Herbrand theorem. That's fine. But that is the idea of this proof. So it's kind of a interesting proof to computation principle. It says the following, that if a function, and that's the main gist of this theories, if a function f is definable by some class of formulas, or formula in this theory, then actually it is computable in C. And that is the correspondence between these theories, feasible theories, and the computational complexity. The idea comes from Herbrand theorem. It's kind of a syntactic trick, more or less. So I'm not going to go over it. But that is the thing. Now, we've seen the setup of feasible reasoning, but what does it give us? So first, let's go to propositional logic. And how does this relate to the first order setup? So we can consider the first order actually in our setup to be really translatable to the first order setup to be translatable to propositional logic. And I give here an example, and that's the following. So if I have, for instance, a sentence that says exist y at most the length, so that's the length of the string x, exist y, that's a number which is at most the length of x, such that, so this is going to be the following, such that xy is true, namely y is a number, is one of the indices in this bit string x. If it is lit, then xy is true, right? So there exists one bit that is in y, that is in x. Anyone can guess how would I propositionally translate this? There exists, this is just a string, x is just a string. And I'm saying there exists a y, either 0, 1, until the last bit, the most significant bit of x, that is 1. So what is this? Yes, big or. Quotient. So it's just a big or, and that's the translation. So I take string, and you see here, so you can see what is basically the essence of this translation, that a proposition, that a first order logic statement can be very easily translated into propositional. If there exists a bit that is 1 in X, then it's just saying that a big or, right? And then I say XY, I give it a propositional variable, and then I say PJX. So it's or of one of them. And the same for all. So what will be for all? Well, for all is end. It's written here. And yeah, so basically I can take this and I can say that if phi x in some class of formula is true for every string length, then its propositional translation, just like I show you in this example, if this was true, right, for every string length, it was always true, then the propositional translation is a family of tautologies, of propositional tautologies. And that's the essence of the translation, more or less. It's just a syntactic translation between first order and propositional logic. And that's the statement here, and that's the translation theorem, and why first order in this setup corresponds to propositional logic. It says the following: if the theory proves phi, then the family of propositional translation has polynomial size propositional proofs, where each proof line is written, well, as a Boolean circuit from the class C. So what have we seen? We've seen that first order logic in our setup corresponds to propositional logic, and if a statement, a first order statement, phi is first order, is provable in the theory, I can translate it into a family of propositional tautologies that have some kind of propositional logic, have short propositional logic proofs. Right. Well, so that is there's another idea here. And the idea is also kind of syntactic. You just take so you have to understand a bit the conceptual distinction here between first order and propositional. First order is about provability, whether something is proved or not. There's no complexity, more so to speak. But when you go to the setup of propositional logic, everything is, all tautologies are provable. The question is whether they have short proof or not, whether they have, in this case, polynomial size proofs, the size of the proof, either the number of lines or the total symbol size of the proof is short or not, parameterized by the number of variables. So that's the distinction, at least this, that you might want to understand between something that is provable or not and something that have a short proof or not. And yeah, here is I wrote the idea, but it's not important. Now, I want to go fully propositional into the area that is one of the main interests of mine. This is, after we did the translation, I can talk about this, the concept of propositional proof complexity. Yeah, so what is propositional proof complexity? You start with a proof system, a propositional proof system, as I said, a textbook proof system that you've learned in first year. And here I gave a very simple one, just a proof with 3 axioms and modus ponens. And then what I've just said is this: you start with a proof, and what is the interesting question? Because everything is provable in propositional calculus, right? It's a complete proof system for tautologies. So every tautology is provable. So what can be interesting there? well, there's a lot of maybe interesting thing, but I think one very interesting thing is what is the size of the proof? So how many symbols it takes to write down a proof in this propositional logic? And that is the main question of propositional proof complexity. And we've already seen that it is kind of connected to the first order setup, because first order setup says the following: if I have a proof, then it is translated into a short proof. Right, that's the conceptual distinction I mentioned. If the proof exists in some precise manner, then I can translate it into a short propositional proof of the translation, as I've shown you how to do an example of how to do the translation. And this brings us to the fundamental open question, one of the fundamental open questions in complexity. Does every tautology admit a short proof? It's not a question, it's well, it's a question. It's not a question that I direct to you. It's going to be quite hard to solve. And this is a big open problem. And I would say it's somewhat reminiscent to the big open question like P versus NP, NP versus co-NP, and so forth. So this is like in the realm of complexity class separations, the big questions. And this is open. So you see such a innocent looking question, whether every tautology admits a short proof in this propositional logic that you've studied in first year is open. So nobody knows how to prove this. Depends on the proof system, but the proof system that I've provided here, this is open, and this is one of the major questions in proof complexity. And or at least conceptually understood that the first order setup give us this kind of question, a way to approach this question, because the first order setup just asked us whether there exists a proof, not if it's short or not. But if there exists a proof, then I would know that there exists a short proof in the propositional setup. And if there's no short proof for some family of tautologies, I would know that there is no proof in the theory. So I get, so to speak, independence proof. A concept, a theorem in the proofs in the theory that is independent of the theory, that cannot be proved, although it is true. And here is Cook's program for proof complexity, more or less. So it says the following. Cook and Recco, and it's from 79. If for every polynomial time verifiable propositional proof system there exists a family of tautologies with no short proofs, then NP is unequal to co-NP. Co-NP, some kind of a dual of NP. It's the complement of NP languages. So basically, this question leads us to and of course, if NP is unequal to co-NP, or not of course, but it's known that if NP by definition, if NP is not equal to co-NP, then also P is unequal to NP. So if we can actually show, you see that this question about propositional proofs is very connected in some sense to P versus NP, because if you can show that for any proof system, there's some hard tautologies, a family of tautologies that do not admit short proofs, then you can separate P versus NP. Of course, it's here, the catch is that there is a quantifier about the proof system, so it should be for any proof system. What I've showed you, the question I've showed you is just for specific propositional logic, but here it's for all. But more or less, it's interesting to see this question, and let's see. I don't want to give the proof. And let's see now a very interesting connection between a first order theory and what is the motivation of this proof complexity, and how the ideas from the first order setup gives us a nice motivation for the question about proposition, the propositional proof complexity. And I'll give you this idea. So, yeah. So the fundamental open question, one of them, the fundamental question of proof complexity, or one of the major questions is, does every tautology admit a short propositional logic proof? And in the limit, if we can show it for stronger and stronger proof systems, I get NP is unequal to co-NP, and hence NP is unequal to P. Now, somebody might ask, but you gave us a specific propositional logic, as I said, the textbook propositional logic from first year. So why is it interesting to show this, to show that the simple propositional logic that I gave you the definition of, there is some tautology that does not have short proof. Why is it interesting for this specific one? If you're asking me to prove in the limit for every proof system, there's some tautology that does not have short proof. And here is a possible explanation that is based on the first order setup. So, okay, we know, and this is a very active live area of proof of complexity and proof complexity, very combinatorial and somewhat algebraic area that tries to prove combinatorial lower bounds on kind of weak proof systems. And we know a lot about this. We don't really have much answer about strong proof system, like the proof system that I gave you in the previous slides. And as I said, the question is, why is it interesting then to try to prove this lower bound on this strong proof system? And the consequence is this. First, it's a concrete lower bound in the direction of P versus NP. So at least morally, it's somewhat interesting because it is a strong lower bound, and at least methodologically, it gives us some tools that might be helpful further on. But also, if we think about the first order setup, then it has very interesting mathematical consequences, and that is this slide. So if there exists a family of tautologies in the proof system I gave you that are hard, that do not have short proofs in propositional calculus, propositional logic, then P versus NP is at least consistent with the theory of polynomial time, the polynomial time reasoning, the first order theory I started with, when C here is P time. Right? So if I can prove a lower bound, this maybe combinatorial lower bound on propositional logic, I actually showed, because of the result that I've described before, that in a first order theory of polynomial time, P versus NP is consistent with it. Or in other words, if it is consistent, it means that there is a model of the world of P time reasoning, such that in this model, it satisfied the theory, the axioms, and P is unequal to NP, right? Because it's consistent with it. And so it shows us that even if P is equal to NP somehow, you need to go beyond polynomial time reasoning to prove it. So that's an interesting mathematical consequence from a somewhat combinatorial looking question about short propositional proofs. Right. So, well, so we've seen something about this, and we had some ideas about the connection between proof theory and proof complexity. And I want to show you just maybe very short examples about some examples about the combinatorial nature of this question and algebraic. And this is quite fascinating because as you see, what I've described up to now is kind of abstract, somewhat aloof, a model of the p-time world that is consistent, such that p versus np is consistent with it. But actually, a lot of work in proof complexity reduces to this kind of very nice mathematics or algebraic and combinatorial ideas. And it's interesting that there is a two-way connection between this kind of algebraic and combinatorial approaches to these lofty questions about models in which complexity theory statements are true or hold in. So maybe I'll give you one or two examples. So this is a very interesting, I hope it is very interesting idea that that students and myself have developed a couple of years ago. And it's this question: can all these problems, this problem at least of the proof system that I provided, the propositional logic, can it be reduced to a completely pure, not completely, but somewhat pure algebraic question about a rank of a matrices? Can I reduce this problem to the question whether some rank have high, some matrices have high rank? And this is a work that I've done about non-commutative computation, non-commutative parallel computation, let's say. So intuitively, non-commutative computation is basically working with, let's say, the following: compute a function of matrices over a non-commutative algebra, let's say 2 by 2 matrices with S processors in parallel and in time that is logarithmic in S, the number of processors. It's very, very straightforward computational model, only that it is algebraic and it is non-commutative. Non-commutative means that, well, x times y is not equal to y times x necessarily. And this model is very weak. A lot of things are known about this. So we know that it is weak, and permanent, determinant, things like this are not computable efficiently in this algebraic model. And what we've shown is the following, is that, right, so so phi has a propositional calculus proof, a tautology has a propositional calculus proof of size more or less polynomial. Let's here it's quasi-polynomial, but think about it as more or less polynomial. If and only if there exists some kind of polynomials that this expression, which is non-commutative, can be computed in parallel with this kind of number of processors. But the moral is the following, that this all, what I've said before, this question about propositional logic that have hard tautologies that do not admit short proofs, reduces to a rank argument. Now, I don't show you the proof, but the way to prove that some function or some polynomial or some algebraic expressions do not have small non-commutative circuits or formulas, as I've described, or you need to use a lot of processors in this non-commutative computation, is a very simple rank argument. You take a very simple matrix and you compute its rank. And if the rank is exponential, you know that the number of processors you need to use is exponential. So this question, as I said, from first order logic reduces in some sense to a question about lower bounding some the rank of some matrices. Yeah, I'm finishing. Right, so just concluding remarks. So we have, of course, combinatorics. I've just discussed something about algebra. Combinatorics also had a huge impact on the proof complexity. A lot of probabilistic methods. There's one very, very active work in both in circuit complexity and in propositional proof complexity. And the last part is, of course, just a couple of notes. What else can we do with logic? So logic and first order logic is a very nice framework for thinking about meta-mathematics, question about what can be proved, not just whether something is true, some mathematical statement is true, but whether we can prove it and what are the axioms or the minimal set of axioms that are needed to prove some statement. And for us, it will be interesting to consider the following question. I have some fundamental question from computational complexity of which I don't know the answer, as most of them are. They are open, but I want to understand its meta-mathematics. What kind of theory, first order theory, is needed to prove this? Or at least can I say that some theories cannot prove these big questions in complexity? And that is a very nice question that can be addressed in the framework of first order logic, the bounded arithmetic, the weak theories of arithmetic I've described. And here is this kind of a very interesting idea, bounded reverse mathematics. Recent years, 1 or 2, it has some kind of a revival. So reverse mathematics, what are the weakest set of axioms that suffice to prove theorems of interest, specifically of complexity? And here are some, well, I've provided some work of mine, but of course there's a lot of other results that I also mentioned in other slides. But if you think about mathematics and algebra, very specific concrete questions about, for instance, linear algebra, computing the determinant. So in a work with Steve Cook, we've gave more or less almost the weakest possible theory that can prove all these determinant, Cayley-Hamilton, and these kind of questions. And well, that's another recent result about randomness in computing. Schwarz-Zippel lemma. It's a work with Albert Atserias. We've provided first constructive proof in this kind of first order logical system of this statement. And yeah, of course, there's a lot of results about the mathematics of complexity. So I'm finishing now. Right. So yeah, we've already discussed this unprovability of NP versus P, starting a lot with Razborov, and then there's some work of Raz from the 90s and 2000, and also results by Rahul and Pich, and work of mine with Rahul and Jiachi Lu, and also a result by Chen Li and Oliveira, a recent result about trying to do this systematic reverse mathematics of complexity. And that's it. So that's the conclusion. Overall, very fascinating area, I think, with a lot of connections, kind of eclectic, combinatorics, algebra, first order meta-mathematics, diagonalization, all these things come together, and in the context of very, very fundamental scientific questions. So it's very interesting, both for people in complexity and people from logic. Thank you. Well, there's not much time for questions. Kusha. Yeah, I think Well, that was the original thing. This was I think that's the paper that I have cited. This one is from Izvestia from 1905. This preceded this, and this I think was oh, no, this was the switching lemma there. Yeah, that's a good question, whether you can formalize it. What is the formalization? Maybe Rahul have done some work on this. Yeah, I think this paper. I don't know. My answer is this. This was not done in a formal setup. That is a very interesting thread of ideas, these barriers by Rudig and Razborov and others, but these are not formal. These are more practical things for mathematician or complexity theories, that they know this argument wouldn't work, but it's not really systematic in the first order setup. So I don't know precisely how to formalize it in the first order setup. It's a good question. Yes, it's definitely one of the streams, but I didn't mention it. Yes. One last question, or? Thank you. Just over the time because I started too late. I sent it to you.